What makes impact failure modeling at high strain rates so hard? Imagine trying to predict how a glass shatters when hit at lightning speed. That's similar to what engineers face when modeling impact failure at high strain rates. It's a tricky puzzle because materials behave very differently under rapid loading. When something hits a surface at high speed, the deformation happens in microseconds, making it hard to capture what's really going on. The faster the impact, the more complex the response of the material becomes. It's like trying to catch a flash of lightning with your bare hands. One big challenge is that materials don't respond the same way at high strain rates as they do at slow ones. They can become stronger or softer depending on how quickly they are deformed. This rate-dependent behavior means we need special models that can handle these quick changes. These models have to include how materials stretch, harden, soften, and even how they heat up during impact. But figuring out the right parameters for these models isn't easy. It requires precise experiments that are often expensive and difficult to perform. For example, tests like the split Hopkinson pressure, bar, or ballistic impact tests need high-speed sensors and equipment. These tests are costly, often taking weeks to set up and analyze, and results can be noisy because of the rapid events involved. Another issue is that impact events are not simple. They involve three-dimensional effects like angles, rotations, and contact forces. When a projectile hits a target, stress waves travel through both objects, bouncing and interacting in complex ways. Simulating this accurately demands powerful computer programs that can handle detailed finite element analysis or advanced methods like smoothed particle hydrodynamics. These simulations are computationally intensive and sensitive to how the model is built. Small changes in mesh quality or damage criteria can lead to big differences in results. Damage and fracture are also tough to predict at high speeds. When a material starts to crack or break, it depends on local stress levels, how fast it's being deformed, and the material's microstructure. Damage models use criteria like stress triaxiality and plastic strain thresholds, but these are often based on empirical data that varies from one material to another. Predicting how fragments form, how cracks grow, and where failure will happen is still a major challenge. Finally, validating these models is a big hurdle. To trust the predictions, engineers compare simulation results with real-world experiments. But because impact events are so variable and complex, matching the two is tough. Small differences in material properties or boundary conditions can cause large discrepancies. Achieving a close match often involves fine-tuning many parameters, which can be time-consuming and sometimes still not perfectly accurate. All these factors make impact failure modeling at high strain rates a demanding task. It requires a combination of detailed experiments, sophisticated models, and powerful computers. Despite advances, accurately predicting how materials will break during rapid impacts remains a significant challenge. This is why ongoing research and development are so important to improve safety and performance in fields like aerospace, defense, and automotive industries.